Hello, my name is Mariana Miranda and I'll be presenting the paper S2Dedup, SGX-enabled secure deduplication. As many of you know, with the advancements in computer technologies, we are experiencing an exponential increase in the amount of digital information. This raises some concerns about the space and cost of data storage and creates a need to explore solutions that try to mitigate this problem. A recurrent behavior noticeable in storage services is that the same data is being stored repeatedly. So, the obvious solution would be to perform deduplication. That is, analyze the stored data and eliminate redundant copies. However, when you're dealing with third-party storage services, it raises some security concerns, so a user might want to encrypt the data before sourcing it. This creates a problem for deduplication because, for example, if we have two users with the same file and they use their own key to encrypt them, this will result in different ciphertexts, so we are unable to perform deduplication. To resolve this issue, the conventional approach is to employ convergent encryption. That is, the key used to encrypt the data is generated from the data itself. This means that identical content encrypted by different users will generate matching ciphertexts, thus enabling deduplication. However, by revealing matching ciphertexts, this results in some security issues and provide considerably less security guarantees than standard encryption schemes. So, with S2Dedup, we wanted to distance ourselves from traditional software-based solutions and explore security solutions based on trusted hardware instead. With our paper, we make the following contributions. We designed and implemented a secure deduplication system that takes advantage of trusted hardware. This system is able to integrate multiple secure deduplication schemes so that we can tailor the deployments for applications with distinct security and performance requirements. And lastly, we provide a novel secure scheme that I'm going to explain later that combines the idea of epochs with the idea of limiting the number of duplicates per block. But before getting to details about S2Dedup's design and secure schemes, we have to first understand what exactly is trusted hardware and why we are using it. Essentially, the main advantage of trusted hardware is that it provides a secure, trusted environment to perform critical operations in an untrusted software environment. We explore several alternatives, but settle on Intel SGX since it is what is most used in both academia and industry. SGX offers isolation by what is called an enclave, which are private regions of memory whose contents are protected from the processes that are running outside of it. It offers attestation as well, which can be used to prove to a user that they are communicating with a specific piece of software that is running in a secure environment. Knowing this, we can proceed to understand S2Dedup's design and how a request is handled. Basically, when a client wants to send their data to the storage server, it begins the process by encrypting it with their own key using a probabilistic scheme instead of a deterministic one. Once this data reaches the storage server, it is sent block by block to the deduplication engine so we can determine if it is a new block or not. To achieve this, it will be inefficient to compare the full content of the block, so instead we use an hash. However, notice that at this step, the data is encrypted by the client's key, so we need to somehow access it in its original form. This is where SGX Enclave comes into play, since it offers a secure environment to access the original data. Basically, we can use the enclave as a remote extension of the client that can be used to process sensitive data. This obviously requires a brief bootstrap stage before the client sends any data to the storage server, where they send their own encryption key via a secure channel to the storage server, and then this key is stored in the enclave. Once this hash is computed, the deduplication metadata is consulted to verify if it is a new block or not. If so, it's necessary to write this block to disk. But first, it is required to re-encrypt the data with the server's key. This step is necessary so that when we want to read back that block, we don't have to keep track of what blocks were encrypted by each user. Once that is finished, we can finally write the block to the storage device. This constitutes our first secure scheme. It essentially relies on enclave to securely compute a block's cryptographic hash and to re-encrypt the data. However, is this still susceptible to some information leakage, since an attacker can, for instance, infer if the deduplication occurred by checking if there are any changes in the deduplication metadata? To mitigate this issue, we introduce another secure scheme that performs deduplication in epochs. This means that the system is only able to take copies for blocks from the same epoch. To better understand this, I'm going to show a simple example. Imagine a scenario where we are at epoch 1 and the same block is repeatedly being written. So, when it is first written, it results in this hash. If this block is written again, since we are at the same epoch, so we are using the same key to compute this hash, it will result in the same hash, so that block is deduplicated. If we change of epoch, so a new key is generated, and that same block is written again, this will result in a different hash, so that block is going to be handled as it is a new block. This establishes a temporal barrier for detecting duplicates, and naturally leads to trade-off between security and space savings. However, the system is not as affected as one would think, since in a real-world scenario we have temporal locality that states that a significant percentage of duplicates are expected to be written in a small time window. Nevertheless, this scheme is still susceptible to an epochal leakage, so to further reduce this issue, we introduced a novel secure scheme that, besides using epochs, also limits the number of duplicates per block. This is achieved by maintaining inside of the enclave an exact counter. I'm going to show a little example. We have here a setup where the limit for the number of copies per block is 5. We already have inside the enclave the counter that has for hash 1 already 4 copies. And outside of the enclave, at the deduplication metadata, the corresponding hash 1A also has 4 copies. If the same block is written again, the counter is going to return 5, and that is at our limit, but it's not over, so it's going to return hash 1A as well. And outside the enclave, it's going to be handled as a duplicate. If the same block is written again, now the counter is going to return 6, and that surpasses our limit, so it's going to generate a different hash, hash 1B. Thus, outside the enclave, it is handled as a new block. This idea of limiting the number of duplicates per block was proposed in the system TED, but they, instead of using an exact counter like we do, they use an estimated one, which can lead to deduplication loss. Nevertheless, we implemented this solution in our system as well, but instead of using an external server like they do, we use the SGX to keep our counter. To develop our prototype, we relied on state-of-the-art tools, namely, as I previously mentioned, we relied on SGX as our trusted hardware platform. To develop the client and the server, we rely on SPDK as our framework. SPDK essentially allows us to integrate a secure deduplication mechanism in the form of a virtual block device. This block device offers a standard interface, which means that it can be integrated with other block devices and offer a richer and more flexible solution. And lastly, we use AES XCS as our block cipher mode to encrypt the data at both the client and server sides. After developing our prototype, we wanted to understand how the different levels of security affected our system. To achieve this, we evaluated our prototype with both synthetic and real-world data. In addition, two types of implementation were tested. One that stores the deduplication metadata in memory and another that does it persistently, so we can assess the overhead of having a fault-tolerant solution. For synthetic tests, we use deduplication as our benchmarking tool, and for the realistic tests, we use three datasets: mail, ohms, and WebEM, which were collected during 3 weeks at the computer science department at the Florida International University. This naturally led to a lot of tests, so now I will only show a few, namely those related with the persistent implementation and realistic datasets to better portray a situation in the real world. Here we have the performance results for the mail datasets. We have 5 schemes. The baseline only performs deduplication and does not offer any security guarantees. The plain and epoch scheme are the first and second that we presented. The estimated is the one based on the system TED. And lastly, the exact one is our novel scheme that combines epochs with an exact counter to limit the number of duplicates per block. Also, since this dataset was collected over 3 weeks, we experimented with different replay speeds, namely, for the mail dataset, we tried a replay speed of 1, 200, and 400. Looking at the results, we can see that for a replay speed of 1, we achieved the same performance for all schemes. This happens because the system is not saturated, so it can easily answer to any request. The same does not happen for a replay speed of 200 and 400, and we can see that when security is introduced at the plain scheme, we get a decline in performance, which is to be expected since it is a price to pay for security and using SGX. For the Epoch setup, the performance maintains essentially the same, and we see a bigger decline for the estimated scheme. This mainly happens because, as I'm going to show in a little bit, by limiting the number of duplicates per block, we have a bigger decline in space savings, so this results in more write operations to disk. And lastly, when comparing our novel scheme with this one, it achieves very similar performance. Now, looking at the space savings, we see that when security is introduced, the duplication gains maintains very similar, which is to be expected since we are not doing anything that directly affects them. For the Epoch scheme, we see a slight decline for the ohms and WebEM datasets and a slightly bigger one for the mail datasets. However, the difference is not much, and that confirms what I said about temporal locality in real datasets, since, as a side note, for the synthetic results, we observe a considerable decline in the duplication for this scheme. The duplication loss is more evident for the estimated scheme, but notice that for our exact scheme, although it also limits the number of duplicates per block and performs the duplication in epochs, is also able to achieve similar or better space savings than the estimated one. This confirms our theory that with an exact counter, we achieve better deduplication than with an estimated one. To conclude, we developed a secure deduplication system based on trusted hardware that is able to support multiple secure deduplication schemes. Also, our novel secure deduplication scheme is able to achieve more robust security guarantees. It has identical or improved deduplication gains and identical performance when compared to the estimated frequency scheme. Lastly, as future work, it will be interesting to further prevent from disclosing duplicates by applying oblivious RAM, expand S2Dedups for other types of deduplication like offline deduplication, or compare S2Dedup schemes with a state-of-the-art solution that rely on conversion encryption or remote key servers to better pinpoint the performance trade-offs of using secure enclaves and network I/O calls. With this, I end my presentation. Thank you for your time.
Thank you. That's a very interesting presentation. We have a question from the audience. Mohammed?
Yeah, do you hear me?
Yes.
Okay, cool. So I wanted to ask about the attestation. So you briefly mentioned attestation in the presentation, but I didn't find any details in your paper. So can you explain which attestation scheme was used in this work?
I'm sorry, do you mind repeating the question?
Sure. Yeah, so on, I think, slide 5 or 6, somewhere you mentioned, when you were mentioning about Intel SGX, so one of the characteristics is the remote attestation, right? So which gives you the guarantees that your code is running inside the SGX protected environment. And
Yeah.
my question was that I couldn't find any details in your paper. So maybe you can elaborate which attestation scheme did you use in your work?
Yes. We did not go into details, but and we did not practically use in our paper, but it's something that can be used, and why the reasons that we chose SGX in our paper.
Yeah, but I mean, there are two main schemes, which is EPID and decap. So which one did you use in your work?
I'm sorry, I used all the schemes, all the secure schemes. I tested all the schemes.
No, I'm talking about the attestation protocol. So when you use SGX, so you cannot implement SGX without attestation, right? So that's the most important part of SGX. So it provides two attestation schemes. One is called EPID, EPID, and another one is decap. So I was wondering which one did you use in your work?
We did not implement the attestation at the time, but we can implement that in our solution.
Okay, so you didn't use
Mohammed,
that.
Let me interrupt you here. In the interest of time, maybe we can move on to additional questions, and you could follow up with Mariana on the Slack channel itself.
Sure, thanks.
Thank you. Do we have any other questions from the attendees? Okay, I have actually one additional question. So, so I was wondering whether it would, whether you envision integrating S2Dedup with a file system as well on top of the storage, or do you expect to use it only as a separate service while directly interfacing with the storage devices?
Right now, our solution is presented as a block device in SPDK that can be integrated with other block devices, and to integrate with other file systems is something that we can explore in the future. For example, the duplication model is independent from SPDK, so that is a separate solution, and I believe it can be integrated with other file system solutions.
Okay, great. Thank you very much. This was an interesting talk, and I'm sure these audience can follow up with more questions on the Slack channel.